Hello everyone. In this short video I want to show you how one can implement the Jones semi-endogenous growth model in Julia. Coming to the agenda of my talk, as already said, we'll implement the semi-endogenous growth model that was published by Jones in 1995. If you don't know what the Jones model is about, or if you've forgotten the details, I would recommend to have a look at the YouTube model that is linked here. Professor Brettner here gives a very good introduction to the model, and I recommend to use it as a fill-up. As already mentioned, we'll use Julia for implementation. Julia is a high-level language, which means it is relatively straightforward to implement the core model logic, and we don't have to deal with low-level implementation details. Julia is used for scientific computing in many areas, and for that it comes with very good support for ordinary differential equations, and that's what we use to implement this model. After having implemented the model, we'll simulate it with different parameters to see the effect of these parameters, and even change them during the simulation to see that effects. Now, assuming you have a pretty decent knowledge about the Jones semi-endogenous growth model, I'll now briefly talk about the details that are important for our implementation. So the semi-endogenous growth model is based on the endogenous growth model by Roma from 1990. And for simplicity, we assume here that there's a constant saving rate S, which means the consumption at time t is just 1 minus the savings rate times total output. That also means that vice versa, investment in capital goods is just the savings rate time total output. We'll further assume that population is growing with a constant rate n, which means that the time derivative of L, the total population or total labor supply, is exactly this constant rate n. Furthermore, we'll assume that there's a constant share of researchers in the population, which means that LA, the researchers, the number of researchers, is beta, this fraction of labor devoted to R&D, times L, the total labor supply. And Ly is the number of workers that are actually producing output, is then defined as 1 minus beta times L. And further down, we'll define the production function that we're using. We'll use a simple Cobb-Douglas production function, where A in time t is the technology that's currently available, at time t. Kt to the power of alpha is the capital stock, and alpha is the output elasticity of capital, and Ly the workers to the power of 1 minus alpha. Now, to implement the model, we have to define two differential equations, and these two differential equations that are shown here are the two interesting ones. So if you look at the first differential equation about knowledge accumulation, here you can already see the two new elements that Chad Jones introduced in his paper in 1995. And these are the two parameters lambda and phi. So going from the start, the change in technology is this parameter delta, which is the productivity parameter, times beta times L. Beta times L is now the number of researchers in the economy, to the power of lambda, where lambda is this duplication externality. So that captures the possible effect that the more researchers you have, or the more researchers there are in an economy, that they might be researching on the same topic, and thus waste resources and actually not finding any new inventions. And the last term is the existing stock of knowledge to the power of phi, and this phi parameter is the elasticity of knowledge production with respect to existing knowledge. So a value of phi smaller than 1 means that there's a weaker effect of the stock of technology on new technology. The second differential equation that is stated here is capital accumulation, which, as you may know, is simply, or is in this simple model, simply new investment minus depreciation. So the first term here is investment. You see S, the constant saving rate, times the production function, so times total output. And since we defined consumption as 1 minus S, 1 minus the savings rate times total output, S, the savings rate times total output, is just investment in capital goods, minus delta K times the stock of capital is depreciation in time period T. Now let's come to the implementation in Julia. First, we'll have to define the core model logic in a function that you can see here. So we'll have to jump a little bit back and forth, but I'm confident that at the end you'll understand what we have done here. So in the first line you see the function definition, and here are the input parameters to this function. We'll begin by looking at the second input parameter u, which is just a vector of the states of the variables. Below here we set a to the first element of u, k to the second element of u, and l to the third element of u. And a, technology, k, capital stock, and l, population, are the three changing variables in our model that we'll look at, and whose evolution we will model here. Du is then the change of these variables. It's an input to this function and also the main output of our function, and it's also a vector containing three elements. The first element is defined here, so that's actually just the change of technology over time t, and is the knowledge accumulation differential equation that we saw on the previous slides. The second element is the capital accumulation differential equation, and the third element is the change in population, which is just this constant parameter n. And the third input parameter to this function is a list of parameters p, and for simplicity we extract all these parameters that are contained in this list to separate symbols, to separate variables, such that we can use them by their simple name in the differential equations below, and you'll see in a minute you'll see why. And the fourth input parameter t is not used in our case here, but could be used in other differential equations. That's why it has to be included. And so please now have a look to the differential equation system that we defined below here. As already said, the first element is the change in the knowledge, the knowledge accumulation equation, and you can see here that it's more or less, or it's actually exactly an exact translation of the differential equations that we saw 2 slides before. Delta is the productivity parameter, beta is the share of researchers in total population, L is total population, which is coming from here, so it's the population at time t, to the power of lambda, which is the parameter that you stated, and A is the technology at time t to the power of phi. So if we skip back, that's exactly the equation that we have here. And thanks to Julia and thanks to Julia, we can use these Greek symbols here, which makes the translation from the differential equations to the programming code even more easier. The second differential equation is the capital accumulation equation. Also here you can see that's actually a word by word, symbol by symbol translation of the equation that we saw earlier. So also nothing new here. And the third element is the change in population, which we assumed is constant. So this change in population is just this constant parameter n that we have defined in this list of parameters p. Now that already defines our Jones model, and we'll now look at the rest of the implementation, and then at the end we can already see a first basic plot of the evolution of our model. So at the beginning here we have to rely on two very big and prominent packages that are maintained by the Julia community, which is the differential equations package, which we'll use to solve our model, and the plots package to plot the solution. In this code block then we'll define some starting values and parameters. We set the initial technology stock at 1, the initial capital stock and total labor supply at 10, and these are then, here are starting values, again in the same order as here, so KL, AKL, and also here AKL, so that we don't mess anything up. The time span, at the moment we just look at 10 periods, so we start the model at time 0 and stop it at period 10. And in this line we define the parameters of our model. So starting with alpha, the output elasticity of capital with a value of 0.3, over to the constant share of saving, or the constant savings rate at 0.2, and at the end lambda, or duplication parameter with a value of 0.9, and in between you see the rest. Now we have the ingredients of our ordinary differential problem already set up, and we define a new ordinary differential problem with this helper function. The first input to this helper function is our model function that we defined earlier. So this is this Jones 1995 function with this starting values. We'll want to solve it over this time span, and we use these parameters to solve it. In the next line, we then call the solver. The solver will, or this function will look at our ordinary differential problem and then decide which algorithm, which solver to apply and to solve our differential equations. The saveat parameter just tells it that that it should save the output at every time step. And sol, then the sol object then contains our solution to the model. And with the last line, we're already plotting the solution with some parameters and with some nice titles and labels. And here you can see a first basic implementation of the a first simulation of the model with these four variables. A is technology, K is the capital stock, L is population, and Y is a total output. So now we want to look at some simulation results where we vary some parameter values and see what effects they have on the simulation output. We want to specifically look at the parameters introduced by Jones. So we want to look at the parameters phi and alpha. So if you simulate the model with different phi values, where phi is, as you know, the elasticity of new to existing knowledge. So a higher value of phi means that the current stock of technology can be better used to generate new inventions or new technology. And you see, for example, with a higher value of 0.9, the stock of technology builds up much faster compared to a value of 0.6, yes, which is then also reflected in an increased total output. And with an increased total output and a constant rate of saving, we see also that the capital stock then builds up faster. So this already is in line with our expectations. If we then test different lambda values, where lambda is this duplication externality, we see a very similar picture. So though the interpretation of lambda is actually the other way around. So with a higher value of 0.9, it means that there's less duplication of research efforts, and a lower value means there's more duplication. So researchers are researching on the same topic, but only one of the researchers can actually make a new discovery or a new invention, and the work of the second researcher is actually then for naught. So when we simulate the model with different lambda values, we see that a higher value with lower duplication has actually the same effect as a higher phi value. So we see that the stock of existing technology builds up faster. There's a higher stock of capital and a higher stock of technology. And the higher stock of technology also means that the workers can produce more, and total output is higher. And with a total output and again having this constant rate of saving, we see that the capital stock is also builds up faster compared to the scenario where we set lambda to a value of 0.6. we can also change the value of lambda of any parameter actually during the simulation. So actually what we're doing here is simulate the model from 0 to 5, and then note what the end values of a, k, and l are, and then use these endpoints as new starting points for a new simulation. And in this new simulation we change the parameter lambda here to 0.3, so to a lower value, which means there's more duplication in research efforts, and this then lets the trajectory of the economy leads then to a lower growth trajectory. You can see that the stock of technology that is available in the economy is actually then does not increase that fast, and we see a similar picture here again for output and capital. And with this, I already want to conclude my talk. In summary, we have seen that this implementation was actually quite simple. We could translate the differential equations almost symbol by symbol from the paper or from the lecture notes to Julia code. However, you need some additional code to produce these nice plots and to do the multiple simulation with different parameters, and then compare these the simulation outputs. You can see the code in the published GitLab repo that I'll present, that I show you a link later on. Overall, the simulation model yields the expected results. So we have tested the parameters that Chad Jones introduced in his paper, and a higher value of 5, for example, leads to existing research being more suitable for new research, and that leads to higher output. And the higher value of lambda means that there's less duplication efforts in research and more efficient research, which also leads to higher output. I think this implementation in Julia can serve as a starting point for more evolved questions. And one question, for example, is how one could relax the assumption of a constant savings rate. How would one go about this? Well, one would have to include the C parameter or C consumption as an additional variable in the economic logic. So the knowledge accumulation equation would stay the same. The capital accumulation equation would then look a little bit different, because then we would not need the constant savings rate, but actually could deduct the consumption, the current state of consumption, the consumption in time t, from total output, and also deduct depreciation, which would give us then new investment, or which would us give then investment. And we would have to then additionally include equation of how consumption changes over time. So the time derivative of big C. For example, one could use such an implementation where R would be the rate of return on assets, rho would be the discount rate, and theta the intertemporal substitution elasticity. That of course depends on which utility function you assume and how evolved your model would be, because you probably want to endogenize R as well, so that the rate of return changes over time. Because if this is constant, then this whole term is constant, and then you would have again a constantly growing consumption, which is probably not what you're aiming for if you want to relax this assumption of a constant savings rate. It would also be possible to model the savings rate or the change of the savings rate itself instead of the change of total consumption, and essentially you would have to substitute C everywhere where you see it now. Yes, and with that, I'm already at the end of my presentation. Thank you for your attention, and here I have my references. You can see that I have posted the implementation here on my GitLab repo, where there's also implementation of the Ramsey-Cass-Koopmans model in Julia and the Roma model, and some further quite interesting links to how one can solve ODEs in Julia. And here is a discussion on Discourse where economists discuss how one can solve boundary value differential equations in Julia. And Professor Timo Drimborn also published some algorithms for solving dynamic economic models with the relaxation method, and it's also an interesting approach, and yeah, also have a look at it. So thanks again for your attention, and see you soon.